Okay, so we just learned the ratio test, and now we're going to apply it in a couple examples and then do some fun exercises and things like that. So let's start with this series right here. So this is my a sub n is equal to -1 to the n minus 1 over the square root of n. And to use the ratio test, I need to know what a sub n plus 1 is. That's basically just exactly what I have here, except instead of an n, I'm going to be putting in an n plus 1. So an n plus 1 minus 1 divided by the square root of n plus 1. So notice here the plus 1 and minus 1 will cancel. I'll just get -1 to the n. All right, so what happens when I do my ratio test? The ratio test asks for the absolute value of a sub n plus 1 divided by a sub n. So in this case, that's going to be absolute value of -1 to the n divided by the square root of n plus 1. That's on top. Divided by -1 to the n plus 1 over the square root of n. And what does that look like? Let's see. If I'm taking the absolute value of -1 to the n or -1 to the n plus 1, those are just going to turn into a positive 1 because -1, the absolute value, that's just going to give you positive 1. And then when I multiply by the reciprocal, I'm going to end up getting the square root of, it's really 1 over root n plus 1 times square root of n over 1. And this ends up giving me the absolute value of the square root of n over n plus 1. So what is the limit as n goes to infinity of the absolute value of square root of n over n plus 1? Well, it equals 1. And the ratio test is inconclusive. So that doesn't help us at all. That was a terrible example to start off with. Ratio test is inconclusive. So that means we need a different way to prove this. And here, the fact that it's got a -1 to the n minus 1 tells me I should try the alternating series test. So is 1 over square root of n decreasing? Yes, because square root of n plus 1 is going to be greater than the square root of n, which means that 1 over the square root of n plus 1, when I do the reciprocal, I flip the inequality. So each time that I get my next term in the sequence, it's getting a little bit smaller. Okay? And is the limit as n goes to infinity of 1 over the square root of n equal to 0? Yeah. And that's because it's like 1 over infinity, which is equal to 0. So we converge by the alternating series test. The ratio test did not do jack for us. Sorry, ratio test. All right, let's try this one. Here my a sub n is 10 to the n over n plus 1 times 4 to the 2n plus 1. Ooh, that's ugly. A sub n plus 1 is going to be 10 raised to the n plus 1 divided by n plus 2, that's n plus 1 plus 1, times 4, 2 times n plus 1 plus 1. Okay, that's going to simplify out to a 10 to the n plus 1 over n plus 2 times 4 raised to the 2n plus 3. All right, so let's look at our limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. And what does that give us? Limit as n goes to infinity, 10 to the n plus 1 divided by n plus 2 times 4 to the 2n plus 3, and that's all divided by 10 to the n over n plus 2 times 4 to the 2n plus 1. Wow, that's ugly. So that's going to be the limit as n goes to infinity of 10 to the n plus 1. I'm now going to multiply this by the reciprocal. I get a n plus 2 on the bottom and a 4 times 2n plus 3. And I'm multiplying that by, and I can actually leave off my absolute values at this point because all these terms are positive. On the top here, wait. Sorry, this should be a n. I messed this up. That should be an n plus 1. That's better. Okay. N plus 1 on top, 4 to the 2n plus 1 over 10 to the n. And this does, it looks like it could be pretty nasty, but it turns out it's actually going to be pretty easy to deal with this. And what I'm going to do is I'm going to line up all of the things that match up. So I've got my like 10 to the n plus 1 and my 10 to the n. So I'm going to put one of those on top of the other. And then I've got my n plus 2 and my n plus 1. So I'll put those one on top of the other. And lastly, I have my 4 to the whatevers. That's 4 to the 2n plus 1 over 4 to the 2n plus 3. So what happens here? Well, 10 to the n is going to cancel out 10 to the n, and I'll just be left with 10 to the 1. So the limit as n goes to infinity of 10 on top. As n goes to infinity, n plus 1 over n plus 2, that's going to go to 1 because I've got the same coefficient in front of the n's there, and they're both the same power. So this is going to be 10. Maybe I can leave the n plus 1 over n plus 2 in here, but we know it's going to eventually go to 1. And then here, 4 to the 2n plus 1 and 4 to the 2n plus 3, this thing on the bottom, I could write that as a 2n plus 1 times a 4 squared, because when I add those exponents, I'll get 2n plus 3. And this 2n plus 1 will cancel with that 2n plus 1, and I'll end up with a 4 squared on the bottom. So what does this come out to be? The limit as n goes to infinity of 10 over 16 times n plus 1 over n plus 2. As we said before, that's going to go to 1. So we just end up with 10 over 16. So what does the ratio test tell us? I did that whole long thing, and looky there. We're in option 1. So that series is absolutely convergent. By the ratio test. All right, go ahead and pause the video now and try exercises 11 and 12 and see what you get. All right, so exercise 11, I'm going to do the limit as n goes to infinity of the absolute value. My a sub n plus 1 is going to be negative 3 to the n plus 1 over n plus 1 cubed. And I'm dividing that by negative 3 to the n over n cubed. My absolute values are basically going to turn all those negatives positive. So this is the same thing as the limit as n goes to infinity. And I'm going to multiply by the reciprocal here. So I get basically a 3 to the n plus 1. And this negative 3 to the n is going to end up on the bottom there. So I'll put a 3 to the n here. And then I have this n plus 1 quantity cubed. And this n cubed, when I multiply by the reciprocal, it's going to go on top. So I've lined up all my pieces. So this is the limit as n goes to infinity. These are going to cancel, and I'll just be left with a 3 on top. And then n cubed over n plus 1 cubed. That right there is going to go to 1 as n goes to infinity. So I end up with 3. So this diverges by the ratio test. Exercise 12. Ooh, a factorial. How much fun. When I do this one, I'm actually going to just, like previously I wrote them one on top of the other, and then I multiplied by the reciprocal, but I can actually do that all in one step. So on top, I'm going to have a negative 3 to the n plus 1 over n plus 1 factorial. And then I'm going to multiply by the reciprocal of this thing right here. That's an n factorial on top and a negative 3 to the n on the bottom. So once again, the absolute value knocks out my negatives. I get the limit as n goes to infinity of 3 to the n plus 1 over 3 to the n. And then I have an n factorial over n plus 1 factorial. So what is n plus 1 factorial? I mean, this first part, the 3's are kind of easy to deal with because that's going to cancel with that. Infinity. I'm just going to get the 3. N plus, so hopefully you all know what factorials are. Like 6 factorial, that's 6 times 5 times 4 times 3 times 2 times 1. So n plus 1 factorial, that's just n plus 1 times n minus 1 times all the way down to like 3 times 2 times 1. So what I get up on top here is n times n minus 1 times dot, 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 all the way down to 3 times 2 times 1. And my n plus 1, it's n plus 1 times n minus 1 times dot, 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 3 times 2 times 1. So all of these, starting at the n, are going to cancel. And I'll just be left with the limit as n goes to infinity of 3 over n plus 1, which last time I checked was 0. So this is absolutely convergent by the ratio test. Yahoo! So a quick review. These are all of the tests we've looked at so far, all the series and tests. And I just wanted to write them all out in one spot. Hopefully you've maybe been keeping track of these on your own. And also tell you what some of the things are useful for in terms of, like, if they have a certain expression or something like that, how you can maybe tell what test is going to work well. So we've got the geometric series. When you use geometric, you can actually calculate the sum. The test for divergence is only really good for showing something diverges. It doesn't show convergence. If you have the harmonic series or any constant times the harmonic series, that's going to diverge. Telescoping series, if you can figure out that it's telescoping, those can be really nice ones because you can actually calculate the sum if it converges. The integral test, we did that in the lab. That one was fun. And that led us to figuring out the p-series, which is also a very nice one if you happen to have polynomials to use. Comparison is really good when you have sine and cosine. The limit comparison test is good for rational expressions. That's like a polynomial divided by a polynomial. Alternating series test, only really useful if you have an alternating series. Also, it's really only good for convergence. It can't prove divergence. And we'll talk a little bit about how you use the integral test or alternating series test to find an estimate for a series as well. And then absolute convergence, again, that's only useful for proving convergence, but that can really be useful with, like, again, sines and cosines. And then the ratio test that we just saw, it's really good when you have factorials or exponentials, or when you've got just a whole combination of a bunch of stuff. That's when the ratio test really shines.